When Albert Einstein first predicted that light travels at the same speed in all places in our universe, he basically imposed the same speed limit on it, 300 km per second, enough to circumnavigate the entire Earth 8 times every second. That, however, is not the end of the story. In fact, it is only the beginning of the story. Surely we're not saying that Einstein was wrong here. There is, however, a process by which particles can travel faster than the speed of light. It seems impossible, doesn't it? Well, watch this video till the end and know more about this. Welcome to Space Discoveries. Subscribe to the channel for every single detail about the new discoveries in the vastness of the space. Also, do not forget to hit that bell icon for new updates. Having said that, let's get started. It is impossible to move faster than the speed of light. During Einstein's formulation of his theory of relativity, this was one of his inviolable postulates, that there was an ultimate limit to speed in the universe and that only massless particles could ever surpass it. All massive particles could only approach it, but would never reach it. According to Einstein, the speed of light was the same for all observers in all reference frames, and no form of matter could ever attain it. However, this interpretation of Einstein leaves out an important caveat. All of this is true only in the vacuum of purely, perfectly empty space. The speed at which light travels through a medium of any type, whether it's air, water, glass, acrylic, or any other gas, liquid, or solid, is slower. Energy particles, on the other hand, only travel slower than light in a vacuum, not in a medium. Using this property of nature, we can go faster than light. Imagine a ray of light that travels directly away from the sun. If there aren't any particles or matter in space, it will indeed travel at the ultimate cosmic speed, 299,792,458 meters per second, or the speed of light. Even though humanity has produced extremely energetic particles in colliders and accelerators, and found even more energetic particles from extragalactic sources, we know we can't break it. At the LHC, protons can travel up to 299,792,455 meters per second, which is as 3 meters per second slower than light. At the LEP, which accelerated electrons and positrons instead of protons in the same CERN tunnel that the LHC occupies, the top particle speed was 299,792,457.9964 meters per second, the fastest accelerated particle ever. In fact, the highest energy cosmic ray clocks in at 299,792,457.9999999999918 meters per second, which would win a race with a photon to Andromeda and back by just 6 seconds. We can accelerate matter particles very close to light speed in a vacuum, but we can never achieve or exceed it. That doesn't mean we can never go faster than light. It just means we can't go faster than light in a vacuum. In a medium, it's different. You can check this out by passing a ray of sunlight through a prism. While light moving through the air might be traveling at speeds so close to the light in a vacuum that it's impossible to see, light passing through a prism bends. Due to the fact that light travels slower in a denser medium, it's just 225 million meters per second in water and only 197 million meters per second in the crown glass. Because of this slow speed and various conservation laws, light bends and disperses in a medium. This property leads to an amazing prediction: the possibility that you can move faster than light as long as it's in a medium where the speed of light is below that in a vacuum. For example, the fusion, fission, or radioactive decay process of many nuclear processes can produce an emission of a charged particle, such as an electron. No matter how energetic and fast-moving these charged particles might be, in a vacuum they will never attain the speed of light. However, if you pass that particle through a medium, even something simple like water, it finds that it's moving faster than the speed of light in that medium. As long as the medium is made up of matter particles and the faster-than-light particle is charged, it will emit a special type of radiation, Cherenkov. Cherenkov radiation is a blue glow that's emitted when a charged particle travels faster than light in a particular medium. The most common place it's found is in the water around nuclear reactors. The reaction inside emits high-energy particles that move faster than light in water, but a lot of water surrounds the reactor in order to shield it from the damaging radiation outside. It's remarkably effective. When a charged particle is in motion, electromagnetic interactions will occur between that particle and the charged particles, making up the medium it's traveling through. These electromagnetic interactions will cause the traveling particle to emit radiation of a particular energy in all the directions that it can, upward, perpendicular to the direction of its motion. However, since the particle emitting the radiation is in motion, and because it's moving so fast, all those emitted photons will be boosted. and rather than a ring of photons moving outward, this particle, moving faster than light in the medium it travels through, will emit a cone of radiation that moves in the same direction as the particle that emits it. The Cherenkov radiation comes out at an angle defined by two factors only. 1. The speed of the particle, v a particle faster than light in the medium but slower than light in a vacuum. 2. And the speed of light in the medium, v of light. The formula is really simple. This means that the angle that the light comes off of is at the inverse cosine of the ratio of the two speeds, the speed of light in the medium to the speed of the particle. There are a few things you should know about Cherenkov radiation. First, it has both energy and momentum, which must come from the particle that's moving faster than light. This means that particles that emit Cherenkov radiation slow down due to their emission. In addition, the angle at which the Cherenkov radiation is emitted allows us to determine the speed of the particle that caused it to be emitted. If you can measure the Cherenkov light that comes from a specific particle, you can reconstruct its properties. It works by setting up a large tank of material with photomultiplier tubes lining the edge and detecting Cherenkov radiation that allows you to reconstruct properties of the incoming particle, including where it came from. Interestingly enough, Cherenkov radiation was theorized even before Einstein's theory of relativity, where it languished in obscurity. In 1888-9, mathematician Oliver Heaviside predicted it, and in 1904, Arnold Sommerfeld, who helped quantize the hydrogen atom, did it independently. However, with Einstein's special relativity in 1905, no one was interested enough in this to pick it up again. Even when Marie Curie observed blue light in a concentrated radium solution in 1910, she didn't investigate what caused it. In the end, it was Pavel Cherenkov, who worked on heavy elements luminescence. As electrons de-excite spontaneously after being excited, they cascade down in energy levels and emit light. Cherenkov noticed that a blue light did not fit within this framework, so he investigated that. Something else was going on. Cherenkov made some aqueous solutions that were rich in radioactivity and noticed that blue light. With a fluorescent phenomenon, electrons de-excite and emit visible radiation. That radiation is isotropic. It's the same in all directions. But with a radioactive source in water, the radiation was not isotropic, but rather cone-shaped. These cones were later shown to correspond to emitted charged particles. The new form of radiation, poorly understood at the time of Chernyakov's 1934 discovery, was therefore named Cherenkov radiation. And it wasn't until 3 years later that Chernyakov's theoretical colleagues, Igor Tamm and Ilya Frank, could explain these effects in terms of relativity and electromagnetism. That led to Cherenkov detectors becoming a useful and standard technique in particle physics. As such, Cherenkov radiation is such a remarkable phenomenon that when the first accelerated electrons were created in the early days of particle physics in the U.S., physicists would close one eye and place it in the path of where the electron beam was supposed to be. When the beam was turned on, the electrons would produce Cherenkov radiation in the aqueous environment of the physicist's eyeball, and those flashes of light would indicate that relativistic electrons were being produced. When the effects of radiation on the human body were better understood, safety precautions were put in place to prevent physicists from poisoning themselves. No matter what, the underlying phenomenon is the same. A charged particle moving faster than light will emit a cone of blue radiation, slowing down while revealing information about its energy and momentum. Although you can't break the ultimate cosmic speed limit, you can always go faster than light unless you're in a vacuum. It just takes a certain amount of energy to do it. And that's it for now. Thank you for watching this video. If you liked the video, then don't forget to press that thumbs up button and also that hot red subscribe button. And we'll see you in the next video.